Okay, Bismillahirrahmanirrahim. So, Assalamualaikum. So, we continue our lecture with lecture 6. This is also belongs to chapter 4, where in this chapter, which is a subchapter of chapter 4, we are going to discuss on how to find pressure and velocity of a discretized partial differential equations, which is come from the governing equations. This by using pressure coupling scheme called simple. For a laminar and incompressible flow, we only require to use x, y, z momentum equations. Uh, that is if it is three-dimensional. And as always, we are also required to use continuity equations as well. So we have two equations, momentum equations and the continuity equations. These two equations is known as the Navier-Stokes equations. Right? It's a combination of these two momentum equations and continuity equations. Usually they will come together. So in these equations, there are only four dependent variables, which is the u, v, w, and p. And we have four equations, which is three comes from the momentum equations, which is the x, y, and z components, and we have a one continuity equations. But actually, for this, there is no independent transport equations for pressure. Right? The implications of this is that only continuity and momentum equations are required to solve the velocity and pressure fields in an incompressible laminar flow. In the continuity equation, you only have velocity field in it, and there is no pressure field term in it. So, in order to link the pressure with the velocity for an incompressible flow, it is important to construct the pressure field so as to guarantee that uh, the pressure that we obtain it satisfy the continuity equations, because for continuity equations actually is not related to pressure. So we are afraid that the pressure that we obtain from the momentum equations is not going to satisfy or fulfill the continuity equations. So once a continuity equation is not satisfied, the solution is not valid at all. Okay, the scheme that is going to be used in this chapter that's used to couple the pressure field and velocity is called simple, which is a semi-implicit method for pressure linkage equations. These are all the steps. What simple does, it is started with by guessing the pressure field, which then will be used to solve the momentum equations, and a pressure corrections equations then will be derived from the continuity equations then used to obtain a pressure field. And this pressure corrections field then is going to be used to update the velocity and pressure fields. And the pressure and the gas pressure field then will always keep improving after iterations. So once for every iterations, we are expecting that the gas field will be close to the correct fields. So before we go into simple scheme, the choice of arrangement on the grid is also important. So there are two most popular arrangements, which is staggered and the non-staggered, or also can be called as a co-located. So for staggered, the velocity components are found at the control volume surfaces. So this is the surfaces of this control volume. So we have a lot of control volumes, and they have like nine, and so we focus on this at the center here. So volume, the velocity field is located or stored at the control volume surfaces. Meanwhile, other variables such as pressure, temperature, and turbulent quantities are stored at the center of the control volumes. So as shown in the figure on the left here, the values of the velocity component u from x direction is located at and stored at lowercase e and lowercase w faces. So by having them stored at the surfaces, it provides a straightforward evaluations of the mass fluxes, which is the du, ds, dv, dy. It is used for pressure corrections equations. Hence, this arrangement provides a very strong coupling between the velocities and pressures. So this will help to avoid any convergence problem, meaning that it is an advantage for this scheme where it is very stable, so it's hard to get diverged. For the non-staggered or co-located, all variables are located and stored at the central node of the control volumes. So if multi-grid methods are used, the co-located arrangements allows the ease of transfer of information between the various grid levels for all variables. So the coupling between the velocities and the pressure is not as strong as staggered because of there's an axis of oscillations in pressure, which will cause the problems hard to converge compared to staggered. So the disadvantage of this initially is the complex in storage because the velocity and the other variables are located at a different part in this grid. Where for the one here, the non-staggered, they are all located at the same locations. Okay, this shows the flowchart of how actually simple scheme works. So you start with begin, and firstly, we are going to guess the initial value for pressure, velocity, UV, and any other properties like temperature and the turbulent quantities. And then we use it solve the momentum equations. We use the discretized momentum equations from what we have learned in the finite volume method discretizations before. And from there, we will obtain the gas U and V. We will update the gas U and V. And this U and V will be used to solve the pressure corrections equations. And from this step 2, we will obtain the corrections equations, the corrections of P, pressure corrections. And we brings all this value to the step 3. From there, we will correct the pressure and velocity equations. From this, we will obtain P, U, and V. So this, without the superscript, this is what we call it as a correct P, U, and V. Only at this moment. And then we bring all these transport properties of phi to step 4. Okay, this is for the case where it is not compressible or it's not laminar or it has temperature. So if we have only two governing equations, if you have only momentum and continuity equations, we solve until step 3. But if we have any other properties that require us to have additional transport equations, we need to proceed to step 4 and do the same things like what we do for P, U, and V to that properties. And then we obtain the correct properties. And then we will check for the residuals. If it is very far away from the correct value, we will assume that it is not converged. So the convergence, usually we have these conditions where if it doesn't reach at a certain threshold, we will say that it is not yet converged. Then we will go back to step 1, where when we go back to step 1, we will replace the guessed value with the one that we found after step 3 and step 4. So we will keep updating the value of pressure, velocities, and other fields, and it will keep improving at every iteration until it reach the convergence criteria. Then we will proceed to end these iterations. So step 1 is solve the momentum equations. So firstly, we guess the pressure fields, P asterisk, P star, we call it. So these two equations are the momentum equations that we obtained from the previous chapters from using the finite volume method discretizations. So here we have a guessed U, V, and P. And with delta V here is the finite control volumes. So A and B here represents the neighboring coefficients of that control volumes, and same goes to the U gas and V gas, and B here is represent the neighboring nodal velocity components, since they are all gas. So the pressure gradient terms in both momentum equations are accepted from the original source term B. So if you look back on the transport equations before, see this pressure gradient, it is belong to the source term. It is together within the source term. So for this case, we extract this pressure gradient out from the source term because we are interested to find the pressure from there. And then the rest of the source term, we represent it in terms of B prime. So step 2, we solve the pressure correction. Step 2, we solve the pressure corrections equations. Here we define P prime as the corrections, P star as the gas, and P as the correct pressure fields, where P is equals to the gas plus the corrected pressure. So same goes to the velocities U and V. So the correct U and correct V is the summations of the gas and the corrections value. So the algebraic form of the correct value can be written similarly like those of gas in the previous slide, like these slides, but we just remove all the star here. So we have A and U without star, the corrected values. Same goes to for the corrections as well, actually. So when you have the correct expressions of this momentum equations, which is without star, then we subtract it with the gas. So this is what we will have when we do the subtractions between these two equations. We will have this equation, and actually this the UP minus UP gas, G is equals to the corrected pressure, and same goes to the velocities U and V. Okay, so the corrected U is equals to U minus U star. The corrected V equals to V minus the gas V, and the corrected P equals to P, the correct P minus the gas P. And then we get this equation. This is the important equation actually. We want to find the corrections pressure first. Okay, in the simple scheme, we approximate by just removing the neighboring terms. Okay, it is because since it is an iterative approach, so we just want to predict the p prime, and so that means that the equation is not. This doesn't have to be physically correct. So if we have it, it becomes physically correct. But we just want to simplify it so that we can just use the iterative approach to solve this. So actually, it's not really that important for iterative approach because eventually we will get the value that is quite close to the one that is physically correct. So by removing this, the neighboring terms, they can be reduced to these equations where we define this du and dv as delta v over which is the finite volumes over the coefficients a. So basically, these are all already known actually. So we omit the subscript p because actually these equations can be applied anywhere. So we just have these equations without the subscript p. And then we differentiating these two terms by x and y, and we add them up. So differentiate the top with x and differentiate this the second terms here, the second momentum equations here with y, and add them. This is what we will get, where we put all the correct terms on the right. So what actually we will have, this term actually is supposed to be equal to 0 because du over dx plus dv over dy is continuity equations, which is supposed to be, or it must be equal to zeros in order to satisfy the mass conservations. So from this, actually, we can use the gas velocity gradients as the mass residual. So we can use this as the convergence criteria, where it must be very close to zeros before we can say that it is the iterations is enough. So actually from here we can obtain the p prime because all of the terms already known. We have the gas velocity, and we know that this is equal to zeros, and we have the value for du and dv. So we can find the corrections p. Okay, in step 3, correct pressure and velocity equations. So once the corrections p is known, the pressure and velocity components will be updated. So for laminar flow, which is incompressible, we will just skip step 4 and we go straight to check for convergence. So if the mass residual is still not converged where it is not close to zeros, we will go back to step 1 and repeat the whole process again. But the new guessed fields in step 1 it will be replaced with the fields that obtained in this step, where in this step we have the new P, U, and V. Okay. So the correct P, U, and V will be substituting the guess P, U, and V. Step 4, solve all other transport equations such as turbulent quantities and temperature. So if the flow is not laminar and incompressible where it requires or it has additional governing equations other than momentum and continuity equations that we use to solve step 1 until step 3, where like for example when we have a temperature field or the flow is turbulent, we are required to use energy equations, and also we have a transport equations, we have a turbulence equations where it is used to find the k and epsilon, which is the kinetic energy and the energy dissipation rates. So we need to do the same thing for all of these transport equations as well. So we need to find the correct value for all of these properties, all of these quantities before we go into the step, before we go for a convergence checking. So similarly, after in the convergence checking, if the residual is very far away from zeros, we will repeat everything from step 1 and it will keep improving until the value is very close to the correct value, and then it will be considered as converged and the process of the simple scheme will end. So this is an example where we consider a case of a steady two-dimensional incompressible laminar flow between two stationary plates. So we have discussed a similar problem in chapter 2 and chapter 3. So by obtaining the solution from a CFD code using a FVM or finite volume methods, so track the progress of the intermediate values of U, V, P and correction P and the mass residuals during the iterative process at a computational nodal point at the center of the channel. So we have center of channel maybe somewhere around here. So actually, for this, it requires to have like when we have like mesh, we have a number of elements. Actually, we have a lot of this value. So for this problem, it's mentioned that uh, this location of this, the one that we are looking for, the field is at the center of the channel. So we assume it probably around here. So by using this step 1 until step 3, because this is only a two-dimensional incompressible laminar flow, so there is no temperature and it's not turbulent, so there is no additional governing equations other than the Navier-Stokes equations, which are the momentum equations and the continuity equations. So we goes only like until step 3 only, and this is for the first one. So basically, this is actually the actual one. I'm not sure what actually the initial guess for P, U, and V at that point before it goes into step 1, step 2, and step 3. So this is actually what the value after step 3 is finished. We have this monitor P and U and V. And then look at the mass residual is still at 10 power of minus 4. So it still like quite far away from zeros, value of zeros. Okay, so it requires more iteration. So and then by doing these iterations too and repeat the same thing from step 1 to step 3 until the 20 iterations from there, we can see actually the mass residuals decrease until a very small value. So we can say that actually this value is quite close to zeros already. Like usually for mass residuals, that is a 10 power of minus 7, which is quite good enough for convergence criteria. So we can say that the value at mass residuals 10 power minus 7, it will give a quite accurate value for that particular field, P, U, and V here. And you can also see the effect of the iterations on that field. Like this is the convergence criteria which is being used for all of this. So it's once we achieve this, we make sure that the mass residuals is very close to zeros. The velocity and pressure fields will be automatically like will follows as well. It will be converged. So as we can see that the change of value of P and U here is no longer like quite asymptotic. It will like remains on the line is quite almost constant when you do more iterations. So it's getting closer and closer and closer to the correct value. So from here, actually this is how you want to determine that the guess value is improving and improving after several iterations and getting closer to the correct value is by the convergence of the mass residuals. And once it's already like saturated or asymptotic to one value, you can assume that it is already converged. And then you can stop the scheme. And if like, for example, if you have a unsteady flow, only after this is converged, you will do the time step, and then you will repeat this simple scheme again until it converged, and then we go to the time step again, and then these things will keep repeating all over again. That's all for simple scheme.